Okay, so so what we have done, we already look into the energy equation, uh, that to look at the four kind of process at dv equal to 0, dp equal to 0, dt equal to 0, and dq equal to 0. So we have reached a few conclusions, such as this equation and this equation. So the next one we're going to do is we're going to uh, do a different one. So this, all of this, coupled with the energy equation with V and T. So all of this is a V and T. So the next, right now we're going to do uh, P and T and P. Okay. Okay. As for looking on the relation of how does the internal energy changes with T and P, we cannot make use of the general first law, whereby the change of internal energy equivalent to the amount of heat transfer with the net work done, because we couldn't evaluate the change of P, because P here is most likely is a function, is due to the change of volume to the function of P as a function of V. So we need to find something that have, instead of P dV, to be V dP in such a way. So to do so, we're going to make use of the relation of the enthalpy. So instead of using making use of a change of U, we will take a look at change of enthalpy. So just make it write down like here, so you can have the understand of the change of enthalpy is defined by the change of change of internal energy plus change of PV, which then give you that U H equal to U plus PV. Okay, so we're going to rewrite the same way what we've done before in terms of internal energy, but we're not going to use internal energy. Instead, we're going to use enthalpy, because of the reason just now, the energy equation related with the change of P couldn't be found in the first law, but we can have it with this, which kind of related with change of T. So the change of enthalpy is due to the change, the rate of change of enthalpy with the temperature at constant pressure, plus the changes of enthalpy due to the changes of pressure at constant temperature. And because we need to relate it as well with the internal energy, so we will combine these two relation to have an expression of H instead of du. So we do this one again. So okay, so instead of just giving it as a general form, we can expand this, so it will become P dV minus now plus V dP. Okay, so del U will equivalent to del H minus P dV minus V dP. So inputting this del U into the first law equation. So I just might copy this one so it'll be more obvious. So initially we get that relation, so I just put this and replace this part of the equation. So I just move this part a bit. To that side, remove the du, and then this one will replace the du that I removed. Make this a bit center. Okay, so we have this equal to du, which previously this one equal to a du in the first law equation. I should have this one. Okay, so this one is this part, and then this one is the other part. So I just make as dh, put it together, so this one can be cancelled, and then what we get is V dP. Okay, so this is what we intended to. Okay, we have the V at a change of dP. Okay, so previously when we are using this, we don't have the dP change. So because we are dealing with the T and V, T and P, then this is be more convenient for us. So we're going to use this new expression of the energy equation. Then we try to put with this relation. Okay, so again we cannot measure the enthalpy. The enthalpy can only be measured with the this relation, internal energy and PV. So we're going to replace this part with this. Okay, so again we make the same kind of form. dq will equivalent to dh minus v dp, and then we try to put all of this together into this equation, which is del H, changes of del H at with the change due to the change of temperature at constant pressure, plus the change of enthalpy due to the change of pressure at constant temperature, minus the rest of this equation. Okay, so if I were to put this together, I can did I miss something? Okay, I missed one thing here. So this should be dP minus V dP. Then it's almost similar to the last form if when we factorize some of the variable here. So this is plus, so del H del P, constant temperature. So factorize the dP here, so this is minus V instead, so this is dP. So at constant pressure, so we're going to check again through all the four processes: isothermal processes, isobaric process, isochoric process, and adiabatic process. So for condition where pressure equal to change of pressure equal to 0, there's no change of pressure, we could reduce this equation again with the same relation, So again, maybe I should reduce this equation first. Let's copy this part, have it rewrite on down here. So this become dp instead. No, this is dq. Okay, dq. So all of this constant pressure, when at constant pressure this value equals to 0, then this we will lose all this whole term, and then we're going to see the same cases that were previously for condition for T and V. So from this we could conclude or compare with the equation that we already know that the amount of heat flow to a system at constant pressure is equal to Cp d, and then we compare this value, we could conclude that Cp is actually equal to, or del T at constant pressure is actually equal to the value of Cp, specific heat capacity, constant pressure. And then we could input back this relation into this, because this is a constant and then this Cp is also a constant, and what we get is Cp dt T minus V dP. Okay, so at constant volume, so next is at constant volume, del V equal to 0. So at constant volume, so I just take the new equation, copy and paste back, put it there, and everything at constant volume. So nothing becomes 0 because there's nothing part that related to the change of volume here. But we can look upon this dq dv regarding on the constant volume. So dq dv at constant volume will give us cv dt, what we the same thing that we established before. So this is at constant volume. So when we put it together, just to make it similar to previously, so I can rearrange the same way, Cp minus Cv. So since that I rearranged a few bits, so we will end up with a extra negative outside here. T minus V. So I already differentiate directly of dt because both of them have dtv, and when I differentiate all of the equation into temperature with respect to temperature, we get this kind of form. Okay, so this is almost similar to what we obtained before. Okay, so right now we're going to look upon the questions. So we know that if I were to differentiate an ideal gas constant at constant volume instead this time, constant volume, so I will get something like this, and then the other side also will remain with R. So the question is, what is the value of this value? So okay, so using the same relation of del H, because again we cannot actually measure the change of enthalpy at the change due to the change of pressure at constant temperature. So we make use of the same identity. So del H del P is T, del P del T constant H, and then another one is del T del H constant pressure equal to -1. So again, what we're going to look is these values. So rearrange which give us, I just want to make you solve okay, so del H negative there, H del T, so invert this as well, del T del P as constant H. So this one we already established before. At constant pressure we obtain that at constant pressure is actually equal to, could be reduced to negative Cp del T at constant enthalpy. Okay, so to determine the value for del T change of temperature due to the change of pressure, Joule-Thomson have done an experiment of a Joule-Thomson experiment whereby an insulated tube using an insulated tube, and then there's a porous plug whereby there's a small porous that allow a certain amount of gases to pass through. So in this side there's a flowing gas with a pressure of P1 and temperature T1, and then at the other side, because the gas is flowing, the gas on this side is due to the gas from this side with this pressure, and then some of the gas passes through this porous plug, and then it will produce a P2 and T2 pressure P2 and temperature T2. So the flow will be from left to right, and then with this condition, ideally, okay, because this is insulated, so Q, and then as the gas expand through this porous plug, the work also equal to 0. There's no work done, and then there shouldn't be also a change of kinetic energy or potential energy in such a way that ideally H1 ideally because of this condition, because there's no change of interaction of this, then the enthalpy should be equal to the same. Enthalpy at this side and the enthalpy on that side be the same, but it's not necessary to have a same temperature at a constant enthalpy, because remember enthalpy is equal to U plus PV. So any of these value, if temperature changes, then the internal chain decrease and the pressure will increase, and then eventually you still get the same value of H. Okay, drop here, increase here, then with that sum of increase and drop, you will eventually could get the same same sum of enthalpy value, thus give you the enthalpy here and here to be the same. But for ideal case, for ideal condition, although that there will be a change of pressure, because here pressure is high because the gas is flowing from here, and then it somehow freely expand to a lower pressure here, P2, because this is a free flow. So the volume here increase, so thus remain the internal energy here to be unchanged. So pressure increase, pressure decrease, because pressure is P1 is higher than P2 because it's flowing from here and then going to the poles to create another pressure P2, thus cause the if I were to label this one as like this, P2 V2, in such a way that the effective pressure here increase, and then based on the enthalpy, the pressure here decrease, and then the volume here decrease, thus cause H1 and H2 to be have a constant internal energy. Have constant internal energy, thus the changes for these two things will be equal. When these two things happen, we go to the ideal gas law. It indicates us that T1 and T2 is equal. So this is for the ideal case. So when this T1 and T2 is equal, then this equation del H del P at constant temperature minus Cp at constant enthalpy. So whenever this gas temperature is the same, this will be equal to a Joule-Thomson experiment, a Joule-Thomson coefficient. If Uj is equal to 0, then it's for ideal. If not for ideal case, not for ideal gas, then this expression will not be equal to 0, but it will equal to a Joule-Thomson coefficient. Okay, so if in an ideal, then the previous equation can again be reduced because of this equal to 0 for ideal case, and then since this is 0, Cp is not 0, then this have to be equal to 0, which then this value equal to 0, and we reduce everything to equal to del P del T constant volume. So this one, when we which I've shown you earlier, that this one is also equivalent to ideal gas constant, and we get the same conclusion what we already obtained before. Cp minus Cv equal to R.